Oops. Okay, so I mentioned when it's a polynomial over a polynomial, is this on? Even if there's square roots just count as half powers, and you incorporate that into analyzing the highest growth terms. So this one, k squared on top, k cubed on the bottom, I kept it simple, but it would apply if you have longer polynomials. You could just analyze the lead terms, the highest powers of k. And so this one is going to be k squared over k cubed, which simplifies to 1 over k. That is the harmonic series. That is a p series with p is equal to 1, and so that diverges. You asked me how I know it's going to behave like that. Because the lead terms always determine the behavior at the highest growth terms. So the terms that are growing fastest always will determine the behavior of your series. So the k squared on top and the k cubed on the bottom are going to determine it, and when you reduce it, it's just k to the 1. The same thing is going to happen here. It's literally, well, it's not literally the same thing. It's a different series, but when I analyze it in that way, looking at the highest powers of k, this boils down to the harmonic series 1 over k, which is a p series with p is equal to 1. This diverges, meaning I know that original series can diverge. This one also diverges as well, because it's literally the same highest growth terms. Now, that's not proof though. That's just me understanding how it's going to work. I now have to prove it for Miss Weezer, and there's two things that can be helpful, but one of them is actually not that helpful. The direct comparison test that's the abbreviation they often use. It's literally comparing their series to a series that's well known. And the series you can often compare it to is literally the series we get by doing this. Now, for the direct comparison, you need to be, and I can rewrite this as the k squared over k cubed. It's the same thing as the 1 over k, but I want to see those same powers as this because I want to determine whether this is bigger or smaller. They're definitely not the same size because that plus 2 makes you have a bigger denominator here, which makes the entire term smaller. So it's going that way, which means that the sum of this series has to be smaller than the sum of this series. I'm going to come back to this. And I know that the series is, I'm going to come back to it. Yeah. Okay, the same direct comparison could be done here. I'd be taking their series with the minus 2. I would compare it to my series, which is everything, the lead terms with everything else stripped away, so the minus 2 disregarded. And I would make a comparison. This is not exactly the same. This is a smaller denominator, meaning I'm dividing by a smaller number, meaning this term is bigger than this term. That goes that way, which means that the sum, the infinite sum of their series has to be greater than the infinite sum of my series. Okay, so now we got to actually look at this, and now I'm looking at this and knowing that this is a p series. I'm actually going to erase this and rewrite it as 1 over k, because that's what it reduces to. I know that diverges because it's a p series, so that means that it diverges, meaning it blows up. Its sum is infinite. And I know that this sum has to be something that is less than infinity. Now, it could be 5, it could be 10, it could converge to 5 or 10, it could converge to any number, or it could be infinite. The fact that it's less than infinity doesn't mean anything. This is inconclusive. The direct comparison test is often inconclusive if your inequality is not going the way that leads you to a definite conclusion. Okay. Analyzing this, my series again reduces to 1 over k. I know that's blowing up to infinity. And their series has to sum to something that's bigger than infinity. So that means this has to be infinity. This is conclusive. Their series diverges. How did I do that? By the direct comparison test. This one, I don't have an answer yet because it was inconclusive. So I don't know. I tried to apply the direct comparison test, but the direct comparison test only is conclusive half the time, depending on which one is bigger than the other. And sometimes it's even hard to tell what the inequality is when you have a lot of powers of k in your polynomials. So the direct comparison test is only useful half the time, and I would even avoid it from the beginning because In this scenario of looking at polynomials over polynomials, it's better to go with the limit comparison. The limit comparison test is going to get me a conclusion in both ways. Specifically, the conclusion that I already drew, that it's going to behave like this. It'll diverge, it'll diverge. And the limit comparison test will be an adequate proof for both those conclusions. Let me show you how it works. I forget specifically how they do it. I'm going to try and guess, but we want to do the limit as k goes to infinity of, and I think they put their term on top, a generic term from their series, and then we pick our own series, which I've already done, and we put the term on the bottom, I believe. It technically doesn't matter, but I believe it's their term on top, our term on the bottom, and we look at that limit. And if that limit is anything that's finite, then A, K, and B, K behave the same way. The way it's written out in the book is if BK converges, then, oh, that's probably, it's not a power, it's a subscript. If BK converges and AK converges, if BK diverges and AK diverges, I'm going to condense that, those two sentences down to they behave the same. Anyway, just any finite value for this limit, and we'll get a finite value. So I'm going to work this out. In fact, I'm going to tell you that it's even more versatile. I can throw in some other powers. Minus 7k plus 5. There we go. What's going new series technically, but the direct comparison test would be real iffy because now that minus 7k and that plus 5 is making it way harder for me to draw conclusions about which one is bigger than the other, and I don't want to bother with that, so I'm just going to do this limit. All right, so I'm going to take their terms. The whole thing, numerator and denominator. That's AK right there. That's a generic term from their series. Below it, I'm going to take a generic term from my series. So my BKs that I chose is this. And the way I chose it was stripping away everything but the highest power terms. All right, I got to work this limit out. I'm going to flip that. When you flip it, what's going to happen is the total degree, when you multiply it out, you don't even have to multiply it out. The total degree on the top will be the same as the total degree on the bottom. So I have a k cubed on the bottom times a 1, still k cubed is my degree. K squared times that k means I'm going to get a k cubed there. So my limit here is going to be the lead coefficients. This one and that one, my limit is 1. And that is enough to draw a conclusion. That's enough to draw the conclusion that A of k and B of k behave the same. I want to mention that 1 over k, I'm not going to write the subscripts, but I don't know if she wants you to. It diverges. I got to specify how I know that. It's by p series with the p is equal to 1 because it's a k to the 1 power. Therefore, that's my symbol for therefore because I'm getting lazy. Their series, the AKs, the series k squared minus 7k plus 5 over k squared plus, sorry, k cubed plus 2 diverges by limit comparison theorem. Always specify what test you've arrived at your conclusions. So I've introduced my own series VK, I've done the limit, comes out to a finite value. I specify that my series that I constructed was a divergent series, and therefore by limit comparison with theirs, it diverges as well. Oh, I forgot to write one. It diverges. Okay, and then you can work the same problem here, and it doesn't matter that the inequality is the wrong way on this one. If I change this to minus, what's going to change? A very minor detail, but not my limit, and it literally will come up to the same thing. So limit comparison is the way to go when you're doing polynomials over polynomials, and limit comparison requires you to compare and do a limit comparison with a series of your own making, and the way you make it is grab the highest power terms, reduce it, and then you can, and it's going to be a p series at that stage, and you can tell whether it converges or diverges. The original series will behave the same way, and the way you establish that is limit comparison, so you don't have to worry about that inequality going the wrong way and it being inconclusive. that's it. That's my summary of how to handle that situation, which is definitely going to be something she puts on there, at least one of them.